Hi there, I'm Jean-François Baffier, and I mainly have two hobbies in Julia. One is programming some packages such as bibliography and static web pages for academicians that I host at Humans of Julia organization. And the second one is constraint programming. Today I will tell you about how to put some constraint in your life with JuliaConstraints. It was a work that we did with Jale, Pedro and Salvador when I was at the University of Tokyo within the Japanese-French Laboratory for Informatics. So, do you ever felt like you have too many constraints in your life? This feeling of not having enough time that pressures you to do more, or to do less maybe. Well, today we will learn how to be under even more constraints with Julia. That did not come out so well, right? Okay, so let me tell you a bit more about Julia Constraints and attempt to provide some common grounds for a constraint programming community in Julia. One thing maybe, what would be constraint programming? So it's a paradigm that can solve combinatorial optimization problems, among other things. One of its key features is that it has a level of abstraction that is close to natural language. When we do problem solving, it often consists in two actions, model and solve. The holy grail of constraint programming is to have the human model the problem and have the machine solve it. All the smartness should be in the solver. Okay, maybe something a bit more formal. To define a CP model, we need a set of variables with their domains, a set of constraints that are predicates over the variables, and an optional set of objectives that we want to optimize for. Let me illustrate constraint programming with one iconic constraint, AllDifferent. It ensures that all variables takes different values. So for instance, in a sudoku game, maybe not everyone knows what sudoku is. So it's a 9x9 grid where we need to fill that grid with number from 1 to 9 with some constraints. And those constraints are the following. Each line needs to have different values, each column needs to have different values, and finally each 3x3 blocks within the grid need to have different values. So this sudoku game can be entirely expressed using only the one constraint, AllDifferent. Here is an overview of the constraint programming ecosystem currently available in Julia. So at the top, the clouds are three constraint programming solvers that are totally independent of Julia Constraints. Then the second line, the two tables, are two types of interface that can be used for optimization solvers, including CP and non-CP solvers. Then comes Julia Constraints with, on the first line, the front end, a set of packages that are the main packages to be used by a normal user. And the last line, internals, are the packages that are mainly there for people that want to fine-tune things. It's within the internals and those front-end things that we can find some package that would be a shared common ground between the different solvers in the constraint programming community in Julia. So let me tell you a bit about the guys in the cloud. We first have ConstraintSolver.jl. It's the first CP solver 100% in Julia by the great open source ES blog owner. You can check his sudoku animated video with Javis.jl as the following URL. It's also the first complete interface with MY and JuMP. So what are MY and JuMP? JuMP is a domain-specific modeling language for mathematical optimization, kind of high level. And MathOPT interface, MY, is an abstraction layer for those mathematical optimization solvers, so not directly done for constraint programming. However, here is a look at how we can implement sudoku with JuMP and ConstraintSolver. So the two first lines are to call JuMP and ConstraintSolver. Then the fourth line is to define the starting grid of the sudoku problem we want to solve. Line 14 is about creating a model for the constraint solver optimizer. On line 16 we add variables, so it's actually as simple as adding a matrix, 9 by 9 matrix, with values that vary between 1 and 9. From line 17 to 19 is just to input the starting solution value into the variables. Then from line 21 to 24, it's a constraint on row and column where all the values need to be different for each row and each column. Finally, from line 26 to 28 is simply the same constraint but for blocks, so the syntax is a bit harder to read. Anyway, once we have defined those variables and constraints, we can just optimize the model, line 30, and retrieve the value at the next line. As simple as that. The second guy in the cloud is CPLEX CP.jl. It's a Julia interface of the famous CPLEX CP optimizer. It's a commercial solution. One of its interesting points is that it uses a constraint programming aware extension of MOI and JuMP. It's still a work in progress, but we can find it in the form of constraint programming extension that extend MOI and GCP that extend JuMP. So I really want us to call the constraint programming extension CPE for ease of pronunciation. CP, GCP include also import-export to usual CP model formats such as MiniZinc, which is great for the constraint programming community. And the last guy to join the crew is basically SeaPearl.jl. It's a constraint programming solver where the search heuristics can be easily obtained via reinforcement learning. Let me show you some example of code for the n-queens problem. So the n-queens problem is just a chessboard on which we want to put 8 queens that do not intersect each other regarding lines, columns, and diagonals. So here is an example of how to implement the model in SeaPearl. So currently SeaPearl is not yet interfaced with JuMP or GCP, but they are working on it. So, but it's still very simple to model. So lines 3 and 4 is about creating a model. Line 6 to 11 is about defining variables. Then line 13 to 21 is something that will be transparent for the user later, but it's to express view on the variables. And finally, you can add the constraint on line 23 to 26 for having different rows for each queen and to not have shared diagonals for upper diagonal and lower diagonal. It's as simple as that. And then you return the model and you can solve it later. So now we have seen what makes constraint programming outside of Julia Constraints. Let's move to Julia Constraints. So if you remember, the 3 previous solvers are mainly backtracking solvers. So they do complete search, which has some advantages. It can find all possible solutions of a problem, and it also guarantees that eventually an optimal solution will be found. However, for some problems, it do not scale so well. On the other hand, for Julia Constraints, the Spearhead package is a constraint-based local search package. It's constraint programming-based heuristics. It's an incomplete method that improves locally at each step, so it's why we call it local search. It has the advantage to be scalable with parallel distributed computing, sometimes even superlinear. It's an anytime algorithm. You can retrieve the solution when you want, when you need it. And in practice, it converges often quicker than complete methods. but with not all the nice guarantees they have. In the LocalSearchSolvers.jl, we actually made a CBLS framework, not a CBLS solver. The idea is that the user can make their own CBLS solver based on the different methods for local search they want to use. This framework makes full use of all threads and processes available in your Julia session. And there is also the CBLS package, the duck in the overview slide, that implements the MOI and JuMP interface. So now if we look at the internals in Julia constraints that are needed to define the constraint programming models, we need to define domains and constraints. So in ConstraintDomains.jl, out of the box you can define continuous domain, so set of continuous intervals, and discrete domains, which can be sets in the sense of Julia or ranges. Thanks to the pattern fold package, any folded pattern, interval or vector can be used with high performance and low memory consumption. So for instance, 1, 2, 11, 12, 21, 22, and so on. We can also make arbitrary domains. It's still a work in progress, but the idea is to be able to construct arbitrary domains such as soccer ball, Tim Holly's fifth clone, and the baguette. You can do whatever you want from that. I have no idea. But the idea, you just need to be able to draw randomly from this arbitrary domain and to enumerate things. So I will show you with the magic square example how we can create variables in the domain. So magic square is a problem where we have a grid, here a 3 by 3 grid, with number varying from 1 to 9. And we want the sum of all of each lines of each column and each diagonal to be equal to the magic constant here, 15. So I will just focus on the beginning of this magic square function. We just get n as an input, that is the side of the grid. We create a JuMP model on line 3, we give the value of the magic constant on line 4, and on line 6 we create x, a grid of size n by n, with values that vary between 1 and n square. And that's enough to define the domain with JuMP and CBLS. Second package that we need is Constraints.jl. It provides you the possibility to express constraints as simple predicates that we call concept over the variables. However, it's not always efficient for CBLS to use constraint defined by concept. So we also provide a way to formulate constraint as error function. Error function as a kind of heuristic that give you an idea of the distance between a configuration and the closest solution. We also provide a dictionary of usual constraints, AllDifferent, where all value needs to be different, order, where all values need to be ordered, and sum equal param, where all the values need to be sum and equal to a parameter. Of course, we do have other constraints that I will not list here. Regarding error function, it's in a way going a bit farther away from the holy grail of constraint programming, where we need the solver to be smart and the model to be easy to do. So we made CompositionalNetworks, a package that smooths the trade-off between efficiency of error function and the ease of use of, well, error functions. We provide the concept, and the computational network will output an error function. It's a glass box neural network that is scalable for the composition of function, not only error functions. There is a talk about it at this JuliaCon, so please do watch it. Now we do have what we need for making constraint programming models. Let me show you an example with Golomb ruler. So we have a ruler of length 6 here, and we want to put marks here, 4 marks, such that no two pairs of marks are the same distance apart. So here we have a solution to that problem, and when we want to model it with JuMP and CBLS, it looks like this. So we define the Golomb function that take as input the number of marks, and we want the length of the ruler, capital L. And on line 2 we create a JuMP model, M. On line 4 we add a variable to it, so here a vector of size n with values that vary between 0 and L, the length of the ruler. On line 6 we add a constraint that says that all marks need to be distinct with the AllDifferent constraint. Line 7 is about ordering those marks, just for the output convenience. From line 10 to 13, we actually ensure that no two pairs of marks are the same distance apart. So it's a bit annoying to read because of the indices, but it's we use a disdifferent constraint that ensures that xi, the distance between xi and xj is different from the distance between xk and xl. Finally, we add an objective on line 16 that allows us to minimize the maximum mark value, that ensures that the ruler that we will find at the end is as small as possible. And we return the model and the variables so that we can solve the model and retrieve the variables value later. Please note that we do have a dispatch function that, thanks to Julia multiple dispatch, is very easy to use and can dispatch to a different modeler, either the JuMP syntax or the raw syntax of the solver, and later I hope to different solvers. Okay, so we have modeled other problems in constraint model. So we have a quadratic assignment problem, chemical equilibrium, network cuts, Golomb ruler, magic square, and queens, scheduling, sudoku, and more. We also do have an associated package called the COPInstances. It's a collection of instances for combinatorial optimization problems. There is no reason it should be restricted to constraint programming actually, but the idea is to provide generators, downloader, and information about known instances for a lot of combinatorial optimization problems to any communities that need it in Julia or even outside of Julia. So to conclude, I will give you a few features and aspects of the journey that we went through with Julia Constraints. So as I said before, Local Search Solvers is a framework that comes with different strategies to improve the efficiency of different CBLS solvers. Among those strategies, you can find a restart strategy and taboo strategy that helps to avoid local minima and to move to other parts of the search space. There is neighborhood exploration, reaction to perturbation for dynamic models, variable selection, and many others. Local Search Solver will probably reach version 1.0 once all the strategy mixing framework is complete, which is likely to be the case soon. From that point, it will enter an optimization phase. One of the big aspects of local search frame solvers is that it was very simple to make it parallel. Why? CBLS solvers scale easily in general, with possibly superlinear speedup. So the only thing we had to do is to create different solver types. So a main solver, that is the main process in Julia, lead solvers, that are the workers, the other process in your Julia session. Meta solver are both of the above, main and workers. And finally subsolvers that correspond to the thread you have available for each process. And then we just had to multiple dispatch a few methods, 3 actually, on the different solver types. So we actually have init where we create a different solver depending if they are main, lead, meta, or subsolvers. Then we have the solve for loop, that is just a loop to basically dispatch the different solver depending on their nature to the different threads and processes. And finally, a stop function, which is basically what a solver do when it finds an optimal solution and or when it receives information from others where that an optimal solution has been found. And that was it. So all is handled with just a couple of macro and methods from base of threads and base of distributed. Really straightforward and easy to do. Still, we ran into some trouble due to garbage collecting and parallel computing. So just to give you an overview of what happened, we were solving Magic Square instances on an HPC cluster, and we ran into garbage collecting troubles. None of the code was optimized at that moment. So if you look at Magic Square 5 collected and Magic Square 6 collected, it's a real time taken by the instances to be solved. And as you see, so the black and the red lines drop in speed with the number of threads. And we even run in cases where 99.7% of the time was spent on garbage collecting. So that was just not doable. So thanks to the profiling tools available in Julia, we were able to extract the effective time for those two types of instances, so MS5 and MS6. And we were actually able to reach super linear speedup just by looking at the effective time. So after that, we quickly patched the solver to have something for garbage collecting around 25% of the time, which is enough to implement the different feature before running into our optimization phase. But that was kind of funny to stumble upon garbage collecting troubles. Finally, I want to thank all the packaging we depend on, especially the following ones. So Dictionary.jl for an even more productive and performant dictionary, Evolutionary.jl for the genetic algorithm in compositional networks, Base in particular for threads and distributed that really work out of the box. It was great. It is great. Mat OPT interface and JuMP for an incredible Julia interface for optimization. ConstraintSolver.jl for showing an example of interfacing the above MOI and JuMP with a CP solver. It was a big help. The awesome folds as a image of Julia Discord server for the logo made with LocalSearchSolvers.jl and many others. So the future of constraint programming, as I see it for now in Julia, is to have the different solver converge to JuCP, to have a common interface for all users. And I hope that we can implement models, common models, share models in constraint models, and in COP instances for the instances. And finally, I hope, especially for the backtracking solvers, actually that have more in common than CBLS, to use things such as constraint domains and constraints to have some common background to build upon. And thank you for following until the end. If you have some follow-up questions, please join me on the chat provided by the kind organizer of JuliaCon. And if you want to ask questions later than that, so without time constraint, you can find me and other Julia constraint people on any of the GitHub repository related to Julia Constraints, the Julia Constraint channel on Humans of Julia Discord server, the Julia Zulip server on the Constraint Programming stream. Also, you can find me on the JuMP Dev GitHub channel with a lot of nice people related to operation research solvers. They were so helpful for Julia Constraint. And I'm pretty sure we can also be reached on Discourse and Slack, well, whatever you want. Bye.